Arshad Magamad from Oracle, and also he's a technical expert in quantum. He used to work for IBM for several years, and he was working with me on developing a lot of algorithms, using Watson kind of system, and he's here with us to share, some of the algorithms, which you can use in quantum. Definitely, he's one of the few guys, who can write very, quickly, the algorithms and all, converting, some kind of a mathematical formula into algorithm, which I have seen in IBM. So I welcome Arshad, to start his presentation.
And thanks, Ganesh, and thanks, Professor Vincent. So, hi, good morning. So, let me share my screen. Yeah. Okay. So you can see my screen, right?
Okay. Yeah. Yes.
Yeah. So good morning also. So as you have in the last 2 days, we have learned about basics of quantum computing and what are the basic building blocks of quantum computing. So now we understand what is entanglement, we understand what is superposition, we understand what are qubits and all theoretically. But now we are going to take a practical use of that, and let's try to understand how could we write some program, how could we write some code to achieve and realize the things in a practical life, but if they are. So there are quantum algorithms. So there are a couple of quantum algorithms which could be used to solve our daily life problems, which could also be solved through a classical computers. But definitely there are some classical computers do have some limitations, but Abhishek yesterday and discussed about it, and this problem could be solved by quantum computers in a very short amount of time. So let's start from a basic thing. What do you mean by algorithm? So algorithm is just a step-by-step procedure, and to perform any calculation, if you perform any operation or to perform any business logic, it's a step-by-step operation procedure, right? So so when you say an algorithm is a quantum algorithm, so when you say an algorithm is a quantum algorithm, so we mean that the algorithm which is being designed to get it executed on the on a quantum computer, right? So I'm not saying that all algorithms which are in the classical, which are applicable in the classical computer, could be executed in the quantum computer too. I'm not saying if there is a very huge difference between the quantum algorithms and the classical algorithms. The algorithms being theoretically written for the classical computers could also be executed, but the main idea is for a quantum algorithm, we have to leverage the features of the quantum computer. So what is the features of the quantum computer? Which is superposition and entanglement, right? So as you understand, for a classical computer, we do have a concept of bits, which is in 0 or 1. But in quantum computer, we have a concept of qubits, right? So the idea is quantum computing holds the idea of superposition. Superposition is an idea where a bit, a unit or a bit could be in any state, in a supervised state, in a superposition state, and until unless it got measured. So it could be infinite state while it's not been observed, and once it is observed or measured, it takes a final state. And entanglement is just a scenario where two quantum bits were entangled with each other and would be in opposite state, or if you know the state of one bit, then we would automatically get to know the another state of another bit, no matter how far they are in the universe. Correct? Now comes the quantum circuit. So what is quantum circuits law? So point is in a classical computer, everything is based on the circuit, right? So if you talk about classical computing, every operation which you perform in a classical computer, and underlying thing is a circuit. So every operation either goes with OR gates, or AND gate or NOT gate or XOR gate or NOR gate. All these are basic gates which are responsible for any mathematical operation into a classical computers, right? Like a NOT gate would reverse the number, AND gate, if the both are same, both are active, or either of the two numbers are active, it would give a positive result. All the mathematical operations are turning around all these gates. And when we combine all these gates, it becomes a circuit. So in the quantum world also, we do have a concept of gates, which is like we have a poly gate, we have a Z gate, we have a C gate, we have a NOT gate. And with the help of these gates, we go and create some quantum circuits, and we do perform operation on the quantum computer. Now, there are a couple of algorithms which runs on top of those gates, which are basic on top of those gates, which we are going to discuss further. Now, before going to the real quantum algorithm theoretically, I just want to go and introduce you the basic platform of the quantum computing. So yesterday what Abhishek explained to install the Qiskit on local environment and simulator, and he demonstrated a couple of things. So now what we are taking it to the next step, we are going to run on a platform which is, I'm using an IBM platform, where we can go and play with our qubit and applying a couple of gates on top of that, so that you can realize how the qubit behaves. So the thing is, you need to create an account on quantumcomputing.ibm.com. So once you create an account, you will get an API token for you. You can go and create it with your personal email ID. So there are two aspects, right? One is IBM Quantum Composer. One is IBM Quantum Lab. So what IBM Quantum Composer is? Let's launch it. I'm just going to launch it now. Correct. So see this. But this is the idea. So what the idea of this is? Let me hide this. Okay. The idea of this is to understand the behavior of a qubit on applying various gates on top of that. So let me explain you. So this thing. So you can see my screen, right? This screen is visible to everyone, right? So this is a platform which is being which is on a quantum composer, where you can see you have 3 qubits in the left. So it's just for simulating a behavior of a qubit on applying different and various gates on top of that, right? So this is a platform. So you can see that here we have different gates on top of this. There we have Hammerdart gate, we have NOT gate, we have C NOT gate, we have Toffoli gate, we have SWAP gate, we have Z gate, we have S. So we have a lot of gates, right? And there are operations like this is a measurement operation, right? This is a Y gate, RX gate. So you can see that here we have a simulation. We have 3 quantum bits: Q1, Q0, Q1, and Q2. And here we are capturing the results, probability of the final result, and this is a Bloch sphere. Bloch sphere is the representation of a quantum bit state, right? So this we can see that we have a phase pi by 2, 0, and 3 pi by 2, and this is a Bloch sphere. So we can see that I have a 3 qubit quantum. I'm taking the 3 qubit. So let's see the 3 qubit in the sense you can see this state is 0, 0, 0 because we have a 3 qubit state, right? So this is a 0, 0 state. So this means we could perform a calculation on 3 bits. Now for the purpose of this understanding, what I'm going to do, I'm just reduce it to 1 qubit only. So I have a 1 qubit. Now to understand this, so this we have 1 qubit. So what is Hammerdart gate? So H gate is Hammerdart gate. So what Hammerdart gate do? It puts the qubit into an entangled state, right? Superposition state means it turns the qubit into superposition state. It goes into a superposition state, and then we got measured. So you can go and drag this Hammerdart gate here and see. Once you put a Hammerdart gate in front of a qubit, it goes into a superposition state. This means it either go into a 0 state, it either go into the 1 state. correct? It's a probability of 0.5 and 0.5 until we got it measured. So once we measured it, it captures it as 1 or 0. So it's a 50-50% of probability. Either it goes into a 0 state or 1 state with a 50-50% probability. Now coming to, there is another gate which is NOT gate. Let's say we are just removing it, NOT gate. So if you apply the NOT gate to this, so this, you can see this is a state of a, right? So if you apply a NOT gate to this qubit, this state, it reverses to another state which is 1 with the 50-50 probability. Sorry, I put a hammer gate only. It should not, wait. This is a NOT gate, right? See, I apply a NOT gate on top of that. So it reverses the whole state. It was 0 at before, and again it reverses to 1. So if I apply another NOT gate, it again reverses the gates, right? So this is what how gate. So the behavior of NOT gate is what it actually reverses the state of 1. It makes 1 to 0 and 0 to 1, right? So it reverses the state. In the similar, if you make it two qubit scenario. So you can see that I can put C0 gate. C0 gate is a gate where input of one decides the output of other, right? So this output of qubit 1 is dependent on the qubit output of qubit 0. So this is just an idea to give you that we do have this platform where you could go and design your circuits, and based on the circuits, you can write an algorithm. So this is the basic building blocks of writing any algorithm, correct? So in the later stages, we were going to write algorithm using these gates, correct? Any question till now? Okay, fine. So we'll go next. So there is another thing which is known as Launch Lab. The Launch Lab is a notebook session kind of thing where you can write your core algorithms. So this would launch a session. So this is a complete session where you can go and launch your Qiskit notebooks and you can write your algorithms here. If you have go and if you launch a new notebook, you can go and write an algorithm, all your code here, and you can execute the things. So now we will go through one by one to all algorithms. So let's come to quantum algorithm, which is Dawkins-Josa algorithm. So what this is one of the algorithm where which works on finding a balance function. So this is so there are two types of functions which is available. One is balance function, one is constant function. So any function which gives a similar output for any input is known as a constant function, and any function which gives whose output got changed with an input is known as a balance function. So it's like an analogy of a toss which could be equally likely to happen. And so this is the Dawkins algorithm is there are two types of algorithm. Dawkins algorithm is only for the two functions, 2 qubits, and then it got extended for the with multiple states, which is named as Josa algorithm. Let's understand this algorithm first. So let's say we have two functions. We have a function which is a 0 and 1. So what we understand with the first thing, if we pass function, if we pass 0 and 1, so this function returns 0, correct? And in the fourth scenario also, if either we pass 0 or 1, it returns always 1, right? So this means that the output of a function doesn't depend on the input. Correct? It doesn't depend on the input. It returns the same value as a respective input. This type of function is known as a constant function. And in the second and third scenario, we see that with 0, it returns 0. With 1, it returns 1. And in the third case, with 0, it returns 1. And with 1, it returns 0. So we see that output of a function do depend on the input of a function. So if you do with the classical approach, it takes 2 steps to identify the balance in the constant function, right? So now let's go and understand with the quantum scenarios. So let's say this is a function. So let's say this is a function UF. So we have an input register and output register, and we this is the first function is we pass in input and we get an x as a cat of x. We give the input of cat x and we get an output of cat of x. Now in the second output register we input cat of y and we have cat of x XOR of f of x. Now what we are trying to do, we are applying the function and then applying the same function to them so that we will come to a original state. Correct? So what we are doing, see, we have cat of x and cat of y, and we apply a function on top of that. We got cat of x and y got replaced with y and then XOR with fx. Sorry. Now again, what we are doing, we are applying the same function on top of that. We see that we cat of x, and then when we do a XOR function with that of itself, we got a 0. Correct? So what we have got a 0, f of x or with f of x becomes 0, and when we apply 0 with the cat of y, then it gives the same result. So what we understand that applying a function and then applying the same function, it comes to a same state. Correct? Now let's understand this with the quantum algorithm. Yeah. Let's open this Doshi algorithm. Now understand. So understand this circuit now. So this is a circuit we have. So understand this circuit, how it works. So what we have done, we have imported the cascade and we imported a histogram and all. So what we have taken, we have 2 qubit circuit, which is quantum circuit with 2 qubits, right? And 1 classical bit. So this means quantum circuit with 2 qubits and 1 classical bit. So understand concept of classical bit. The classical bit. So there is a qubit, right? So qubit is in superposition state, and if you want to understand and know the state of any qubit at the end, you have to get the state stored into classical bit. So with every qubit we have taken into the algorithm, we have to take a corresponding classical bit also to state. So you have to store the state of the output of the qubit. So what we have done. So what we have to identify, see not this CZ is a balance function, right? We have to identify a balance function out of that. So how this is a balance function? You can see this is a function which is a balance function, means input is 0. The output of a function depends on the input qubit. So this is a balance function. So we are trying to find out the balance function out of this. So what we are doing, so what we have done, we have taken a circuit of 2 qubits and then put a Hammett gate at first qubit, put a XOR, this is H1, this put a X gate at another circuit, then put a Hammett gate at second circuit, and when we draw this, it comes out this is a output of this thing. We apply Hammett gate and X gate and then Hammett gate with it. Now what we have done, we have put a balance function out of this. This is a CZ. So what we have done, we have put a CX gate on the second qubit and put a barrier and then put a Hammett gate on top of it. Hammett gate in the sense we're applying the same function again after putting the balance function, and then once we measure it, so when we measure it, we draw the ampere. So this signal, so this is a measurement, right? Now once we apply this gate, we are putting some measurement here. So once we measure it, it captures a final result. So and we then push it to the simulator, custom simulator, and once we find it, it gives me a one which is a balance function. Okay. So this gives an output which is a balance function. Now, what we are going to take, we are taking this to a final. This time we run into the simulator. Now we are going to put into a quantum computer. Now there are two things. So we can go and execute our circuit. So this becomes a circuit. Now this becomes a circuit. Now once the circuit is executed into simulator, we are going to push this circuit into the quantum computer, actual quantum computer. So we do the same thing which we did yesterday, load account, which we did yesterday when we run it on a local basket. So we just load an account. We have API key already been provided. We load the provider first, and we find out key what all providers are available right now. We see that these are the providers available with how many qubits and which are in the queue, and how many qubits are available for those providers. So we just take IBM Quantum, which is this one, and we take this as a backend, and we executed this 1000 times this short. So short is an epoch, how many times we want to execute this, and we executed it and we short, and we identified it when short, it 95% it identifies this as a balance function. So one is a balance function, 0 is an unbalanced function. We see that once we execute it count it, and it detects it as a C0 as a balance gate, and it detects as a balance function. This is a one-shot algorithm. So this is how the Gaussian algorithm works. Now coming to the Benjamin-Vazirani algorithm. So this is another algorithm. So this is another algorithm to guess. Let's say, take an example, to guess a number, which if you have given a number, and if you want to guess what it is, then how it will work. So we see that Gaussian algorithm takes big of one runtime complexity, means it able to identify the balance and balance function at a one shot only. Correct. Now what we are taking another algorithm which is, so let me understand the oracle. So oracle is a black box function which takes input and gives them output, right? So it's so output again 0 or 1. It could be 0 or 1. So let's say, taking this example. So let's say I think of a number, and I just think of a number and ask my friend, which is let's say a 7-bit number. Let's say I think of a 7-bit number, and if I ask my friend to, can you guess the number? So it might guess 0000 first time, then it might go and guess 00001. Third time it could go 001001. So there could be 2 to the power of 7 possibilities, and it has to make this 2 to the power of 7 attempts to get the right number. It might be possible that person has to manually, it would take 2 to the power of 7 attempts to guess the right number. Now, if the same problem is given to the classical computer, so if the same problem is given to the classical computer, it would take only 7 attempts. Reason? What it will do, it will put an AND gate with that number and try to find out where it got 1. So it is scanned through, it performs an AND operation between each and every number, and once it got the exact result, it has to perform it 7 times only. So the classical computer has to make it a 7 times operation to perform this operation, but a quantum computer would take a one-shot thing to guess the number in the right way. So let's take an example. So this is so this is the algorithm for Bernstein-Vazirani algorithm. So what again we are doing the same operation. We are inputting twist skip. And so what is our secret number? Let's say we have a secret number 1000101. So this is our secret number, which is 10000. Now we need to ask the quantum computer to guess this number. Now we would go and create a quantum circuit, which is we are taking 8 qubits and 7 classical bits. So we create a quantum circuit with 8 qubit now. Now this is, we are applying hammered gate to all the 8 qubits. So the reason for hammered gate, the reason for applying hammered gate is we are pushing those qubits into a superposition state. So till now we are not putting anything. We are pushing the qubits to a superposition state, and so that it go and start the calculation. So we are putting hammered gate on top of it, and we are 7 bit. We are putting a NOT gate, X gate, and then we are again putting a hammered gate on top of that, and we are putting a barrier. So once this code got executed, so this is what we have. Till 7 bits we put a hammered gate, and 7th bit, see, we have 8 bits, right? We have 7 bits, right? We take a 7 qubit, we take a 0 to 6, 7 qubits, and we put a hammered gate, and then the last qubit we put a NOT and hammered gate, we put a barrier. Now what we have to do, we are putting CX gate to the 1 bits, right? So we have first bit, sorry, 0, 0, second bit, and 7th bit, right? So what we have put, so 6th gate, sorry. So we have put a 6th gate with 0, 3, 7, 6. So whatever bits we have won, we are just putting a CX gate on top of that, and then put a barrier, and then again applying hammered gate on top of that. Now what we are doing, we are just measuring. Now we are putting a measurement now. So what we are doing, we are trying to make a measurement of all 6 bits and putting the result into a classical bit. We put, so what we have done, we have put CX gate on top on the desired bits, and we then measure all the qubits and then put into classical bits. So what we have, and we run it on a simulator, and with a one shot only, we are able to get the secret number. Correct. So just understand that we with a normal approach, with a mathematical approach, it took to the power of 7 guesses you have to make, and with the classical computer approach, it requires at least 7 operations to perform this. And but with the quantum computing, it only would take one shot with 7 qubits, and we are able to guess the right number. Correct. So this is what Bastien-Vazirani algorithm. Right. Now the third algorithm comes. So any question till now? Anyone? Okay. So we are going to the next thing. What is Shor's algorithm? Now Shor's algorithm is a potential threat to the security, I would say. So what do you mean by an encryption? So what do you mean by 126 RSA encryption, 128-bit RSA encryption? So let me try to understand that finding a prime factor of a number is a highly complex problem. Correct. So if you have a number 15, if I ask you to find a prime factor of this, you got 3 and 5. Correct. Now if you have a very bigger number, classical computer could take thousands of years to crack the prime factor of that number, literally. So what RSA algorithm is dependent on that. So what RSA 128-bit is works on it. So 128-bit RSA algorithm says that if we have a 128-bit number, one need to find the prime factor of that number in order to break the algorithm. Correct. The whole crux of the RSA algorithm is until you find the prime factor of that algorithm, you cannot break the algorithm. Correct. RSA algorithm. In today's classical computer, breaking a 128-bit number and finding the prime factor of a 128-bit number, or 256-bit number for a classical computer is a 1,000-year problem. It takes 2,000 years for a classical computer to find the prime factor of 256 bits. Now, so the whole idea is encryption is not a problem of security. Encryption is a problem where to solve that problem, it takes much more time for today's computers. That is the reason it is secure, correct? So if anything comes which has a capacity to make that calculation in a limited amount of time, in a real-time amount of time, all the encryption would got failed, correct? So the Shor algorithm is same thing only. Shor algorithm is same thing only. Shor algorithm identifies the approach to find the prime factors of any number with some modular arithmetic approach, and then calculate. So I'm not saying that Shor algorithm should be only a quantum-based algorithm. It's a simple algorithm which could be on a classical computers also, but it would take a huge amount of time to get the result in a classical computer. Correct? So let's understand what is a Shor's algorithm. Shor's factorization algorithm is proposed by Peter Shor. So this is a person and who has proposed and developed this algorithm. It suggests a quantum mechanics allow factorization to be performed at polynomial time and exponential time. So you can see from this graph. So if you have to find the prime factors of any number, it took an exponential time for a classical computer, right? It goes in exponential way. As the number of digits increases, the growth of time complexity of that algorithm is exponential, correct? But with the Shor's algorithm, the time complexity becomes a constant with quantum. So we can see that the whole encryption body, the whole encryption logic is relying on how fast we could, or how fast we could find a prime factor of a number, and until unless we do have a private key. So I forgot to add. So the encryption happens with a public key. Encryption happens with a public key, and then decrypted could be happen to a private key. So private key is nothing but the key which identifies, which tells this, these are the prime factors for this number, and with this number you could go and break this center. So if you don't have the private key, it's very, very difficult to guess those factors, right? So what this algorithm RSA whole works. So let's understand the whole idea behind it. So the algorithm is given an odd composite number. We have to find an integer strictly between 1 and n that divides n. So what is, so if you have a number which is, let's say 15, so we have to find an integer 3 which divides n. So prime factor of 15 is 3 and 5. So we have to find some integer where which divides 15. So 3 also divides 15 and 5 also divides 15. The Shor's algorithm works on two parts: conversion of a problem, or factorization of a problem, finding a period. So if you see this, so there is a repetition. So if you take any number and you take a modulus of that number with let's say you have to find a prime factor of some number. So what do you see? When you do take a modulus of that number with the sequential, we see a pattern being repeated. Like we take 2 mod 21, we have 2 to the power 1. 2 to the power 2 is 4 mod 21. We have 2 to the power 4, 16 mod 21. When we come to 2 to the power of 6, the pattern got repeated. So we see that when we take a modulus of a number with a sequential, where a pattern got repeated. So idea is that we have to find that pattern. And let's say to come up to algorithm. So I'll explain through this code. So this is a basic algorithm. So we have to choose any number between, let's say we have to find a prime factor of n. The Shor's algorithm says choose any number, let's say r, which is r should be less than n definitely. If your prime factor of 15 is 3 and 5, then r should be less than, so that they can be co-prime with each other. The quantum computer used to determine an unknown period. So we have to find a period, right? I told the period such that a function of r and n with x with r to the power of x mod n P, and we have to find this modulus for all the integers, and if P is an odd integer, then we have to go back to the first step. And if P is, so we have to see, understand this. For any number which is a prime, which is, we need to find a prime factor. This is a R of P power, we have to identify a P such that R to the power of P minus 1 multiply R to the power P divided by 2 plus 1 becomes N. So these two numbers becomes a prime factors, and we have to identify the P for that only, correct? And if the value of P, R power P divided by 2 plus 1 is 0, then go back to step 1. And we have then ultimately we have to come, once we find the right P with the quantum thing, we have to find a GCD, greatest common divisor of that number with that of N, and then compute the DD is the should be the final answer. So let's take this with an algorithm here. Sorry, Shor's algorithm. Classical. So I'm telling you to solve this problem with the classical computers as well as a quantum computer. So let's say we have, this is the classical approach of solving a Shor's algorithm. We have an import method which is matplotlib, and this we have to find a prime factor of 15, and let's n equal to 15. So we are implementing the same algorithm here. We are taking set something in the range of this, and we are trying to find the series, right? So we are taking a modulo of n with the z0, and we try to identify the sequence where this got repeated. The sequence got repeated. We identify that at 4, p equal to 4, we find that this modulo has been repeated. Now with this p equal to 4, we feed r to the same algorithm here. Where is this one? Now what we are saying that if R is even, so if R is even, then we have to again perform the same step. If R is odd, if R is even, then we have to perform modulus of this operation and identify the at the last we have to find the GCD of the two numbers, right? So what we have to find the GCD of these two numbers and finally get the results which is equal to 5 and 3. But this algorithm for a bigger number like 256 bit, it could take a tremendous amount of time which could not be feasible in terms of classical computing. But this is a classical way of finding any prime factor. So understand this is a classical way of finding any prime factor of a number using a modulus approach. And with the Shor quantum algorithm, so Qiskit comes with a Shor implementation, Qiskit comes with a Shor algorithmic implementation. So we just have to import the Shor algorithm method, and we just take an instance of thing, and we take n as an input, and we just execute this quantum on a quantum instance, and we just have to call Shor.factor, and it go and give the results 3 and 5 as a factor of that. So what Shor is the sole algorithm in this is got implemented in the quantum computing in as a function, and we could use this algorithm to find the prime factor of this. So idea is the prime factor, the objective of prime factor is the business reason for doing this is what we are trying to do. We have to identify in future, means if you were able to identify the prime factor of a 128-bit encryption or 256-bit encryption, the whole security systems and whole credit card systems could be compromised, because we do have a real-time implementation. You have a real-time systems which could break the security, and all these things could be compromised, right? So that is the whole idea of this Shor's algorithm. Okay. Now coming to the last algorithm, which is the Grover search. So what is Grover search? So So Grover search is another algorithm which is a practical thing, which is basically for searching a number, right? Searching a number, or more practically, you could say searching something into a database. So in a database world, we have millions of transactions happening, millions of records happening. Then it's very difficult to find the right record uh, in a mean amount of time. So that is what the Grover's algorithms comes into the picture. So look, let's suppose we have a sequence of number which is, let's say, an array, and we have to find a number which is a w, right, which is in some position, right? Now so how do you do in a classical way? You go, suppose if there are 1 lakh record, you go one by one to each and every record and then check this is correct, this is correct. So maximum it could take n complexity of 0 of n, and minimum it could be found at the first place also. So on an average, this search algorithm in a classical way usually takes n by 2, O of n by 2. So think of this, if it is a very, very huge record system, very, very huge database, it would be very, very difficult to find a record out of billions of records, billions of records in a table, right? So in order to optimize this, we use a Grover's algorithm. So Grover's algorithm works on the reflection circuit, kind of a reflection circuit also, and we reduce the whole complexity of this algorithm to big O of under root n. And it utilizes superposition and phase interference. Superposition means amplitude amplification. So there is a concept of amplitude amplification. So if there is certain qubits who are in winning state, it do superposition interference. So what do you mean interface interference? What is phase interference? So phase interference is something, if two qubits are running into a same phase, then if this interference is positive, then definitely the phase would amplify, correct? And if the two waves are into opposite direction, definitely those phases in opposite direction, they will cancel each other. So this is what this noise cancellation works, right? It go and cancels the phases which are in opposite to each other, and it's stimulates. So this concept works on a amplification, amplitude amplification. So it takes if any qubit moves in the same phase direction, it goes and amplifies the state, and then that amplified state comes at a winning position. The amplitude amplification is a procedure that increases the probability amplitude of the value to be searched and decrease the rest of the probability. So it finally the highest probability value which is in the winning state would get amplified, and rest of the amplitude got suppressed, decreases. So let's come to short algorithms implementation ones. Sorry, Grover's algorithm. So this is Grover's algorithm. So same thing. So let's say we have first take the classical approach, and then we will take a quantum approach. So let's say we have a number which is 5, 4, 6, 9, 1, 2, 3, 7, 8, 0, and we have a winning position as 8, right? We are giving a winning position as 8. I explain you what is oracle. So oracle, we in a quantum world, we define it as a black box function which could result to take some input, give some output, right? So we define a function which is oracle, where we say our winning number is 8. If the winning number is 8, we identify the response is true, else the response is false, right? What we are doing, we are going to loop through this list and pass the number one by one, and as soon as we get the winning number as 8, we got a true from Oracle, and it breaks the loop. So we find that winning number is 8 and execution count is 9. So it executed, execution complexity is O of n by 2 or O of n, we can say, right? It takes 9 iterations to find that 8, right? Now taking into same thing into quantum thing. So let's create an Oracle circuit. So our winning number is 11. So our winning number is, let's say we have to find a 1 if we have 2 qubit thing, we have to find the cat of 1 So 1 would be our winning position. So first thing, we have to create a quantum circuit. We have to create a quantum circuit with 2 qubits. We name it in Oracle circuit here now. Now Oracle circuit, we apply CZ gate to both and then convert to a gate. So we are, thing is that we apply some gates and then convert to a gate means you are transforming the whole thing as a single gate, correct? So like, let's say ki adder circuit, we have an adder circuit, right? So adder circuit is what? Is a combination of AND gate, OR gate, NOT gate, right? So when you combine these gates in some fashion, it becomes an adder circuit. So it becomes a gate, another gate, correct? But it do build from a building block, some building blocks, right? So CZ and all. So what we see that, so these gates are the building blocks, like AND gate, NOR gate, NOT gate. These are the building blocks, right? So we can go and form a bigger gates, bigger circuit out of them, and then completely combine them to form a custom gate, which you can name them anything. Okay? So this is what we are doing. We are taking Q qubit, we are applying CZ gate. CZ gate is 1. So what we are doing, I tell you. What is CZ? Control gate modifier. Oh. See, why this is CX, not CX. This is okay, right? So we apply a CZ gate here. So this is our gate we are applying. So we apply a CZ gate here and then convert it to a gate. So now what we are doing, what we have created is an Oracle circuit. This Oracle circuit is act as a reflector kind of, or it swaps the positions of this qubits, and then we apply this Oracle circuit to a main gate. So main gate, you see this is 2 qubit. We create a quantum circuit with 2 gates, and we apply hammered gate to and put an Oracle circuit in front of it, right? So this is what gate we found. Now we use an reflection circuit. So this reflection circuit is responsible for amplitude amplification. So what we created another circuit which is a reflection circuit. We created a hammered gate, then put a Z gate and CZ gate, and then hammered gate. This forms a reflection circuit for us. This reflection circuit is responsible for amplitude amplification. And we put this reflection circuit into the main gate. So what we see, this is hammered gate is a main circuit. Then we put a Oracle circuit and put a reflection circuit, and then we finally measure it with line by line. We finally measure it, and from the measurement we put it into the simulator, and we identify that this is our winning probability, and this 1 we got the winning state. We got the quantum with a 1 shot only. It able to identify the quantum winning state of the quantum bits. Correct. Now there is another approach of another implementation of Grover's algorithm, which is known as say you have hosting a party. So this is another use case of Grover's algorithm I am telling. So suppose you are hosting a party where you have some constraints, right? So either James and Lars would come, or Kirk and Bob would come, and not Lars and Bob. Means this is the combination you have to take. So if you're inviting James, you cannot invite Kirik. And if you are inviting Kirik, you have to invite Rob. And if we are inviting Kirik, and then you should not invite Rob. So this is a kind of a combination. So if you think of such combination, right, we have to, if you invite someone, you have to invite them also. If you invite someone X, you don't have to invite Y. And there could be a number of combinations. There are 3 combinations. But if you talk about a huge such combination, it would take a huge amount of time for a classical computer to find all the right combination and get you the output. So Grover's algorithm could solve it very easily. Let's understand this. It is like a dinner party. So understand it. So same thing what we are doing. We are importing a phase library here, amplification problem. We are importing the Grover's algorithm. So what we put our conditions, right? So James and Lars would come, or Kirk or Rob will come, and not Lars and Rob. So this we just transform this complete thing, this combination here, and then we push this function. This becomes a phase function now. This function to an application problem. And then we send this to a simulator, right? And this is our Grover function, which is an inbuilt of Qiskit. We push this thing to a Qiskit thing, and then Grover.amplify. This one goes and amplify in the results. So what it finds? So when we find the results, we see we find this thing. So think of this direction, right? It gives the results like this. So this is a probability of this. So 0, 0, 1, 1 means, think of James Kirk. So think James 0, 0, 1, 1. So James Kirk, Lars Rob. So we can think of like 0 left to right, right? So let's say 0 would be James. The leftmost position would be James, then next was Kirk, then third is Lars, and then Rob. So this is a probability, right? So how this comes? So first thing, so let's say 0 is James' position, second position is Kirk, third position is Lars, and fourth is Rob. So you see, first is 0, 0, 1, 1. It invites us only James and Lars would come. Second combination would be 0, 1, 1, 1. So James, Kirk, and Lars would come. 3 would come. Third combination 1, 1, 0, 0. Yani Kirk and Rob only will come, and fourth position 1, 1, 0, 1. So James, Kirk, and Rob. So these are the 4 people. These are the 4 ways we can go and invite the people which would satisfy this constraint for us. Which would satisfy this constraint for us. So these are the 4 probabilities it goes and identify for us. That in this way, either we can go and invite James and Lars, right? James, Kirk, and Lars, James, Kirk, and Lars, James, Kirk, okay, and Lars, right? Kirk and Rob, we can go and invite, and James, Kirk, and Rob, James, Kirk, and Rob. Correct. So in this way, we identify that this is the 4 combination. It goes and identify how we can go and invite people in the dinner party. So yes, so unstructured data, no. So Grover's algorithm, we need to transform the unstructured data into form of a structural way so that we can put into a quantum algorithm. So there are a number of ways we could transform the unstructured data into a structured way, and then we can go and put that data into the Grover's algorithm. That is point. So unstructured directly, you cannot go and push into that. Any other questions to anyone? So basically, I am done with all those things. So we are open for Q&A. So if you have anything, then we can take a discussion. Else, I'm I'm done with all the algorithms here.
So, Arshad, thanks for the presentation, and really very useful for people who wants to learn about the algorithms level. All the 5 algorithms are very interesting. So, how one can apply in a classical computing these algorithms? Is it possible? Like, is there a way you have anything with the existing computers? People can try it out.
See, we can see the point I raised in the earlier. So these algorithms are basically designed which could use or leverage the superposition and entanglement phase of a quantum computing. So definitely we can use into the classical computing also, which is already being used. All these problems and all these issues are already being, but with this quantum algorithm, we are mainly focusing on utilizing or leveraging the superposition state of a qubit. So to solve the problem. So in a classical computer, we could not do the superposition entanglement state. We could apply this on a classical also, but it could take some more time for you, for the CPUs.
Is there a simulator available which could simulate like kind of a quantum entanglement or superposition?
Yeah. You can use a quantum simulator. A quantum simulator is itself could simulate you everything. So if you look into this thing, this thing, it's completely a simulator, right? It tells you it tells you what is the what is the state of a qubit on applying each and every gate. Right, so if you put a Hammerdad gate, so if you see that if you put a Hammerdad gate on this, let's say you put a single qubit system here, and if you put a Hammerdad, so I tell you quickly. So you see this. So this qubit is in the 0 state, right? So Hammerdad gate is ultimately putting the qubit into an entangled or superposition state, right? So this is simulator. If you put a Hammerdad gate on top of that, it brings the whole qubit into a superposition state. Correct? It brings the whole, so you can see that it goes into state 0 with 0.5 probability and state 1 with the 0.5 probability. So it ultimately transforms the whole thing into the superposition. But this is not executed on a quantum computer. This is executed on only a simulator only.
Okay. So but how the students and the faculties can access this kind of facilities? That's the overall question here.
They can go and create their own IDs and they can access it. Means this is, I think, general for it's a public open things. Anyone can go and register things and do the things, right? You can go and IBM do provide you. I registered with my personal ID and I able to access all those things. So they are providing this for practice purpose. They are providing some like Google is giving Gmail and G Drive access to general people. Then IBM also giving the access to this right now. So I am using my public personal email IDs to access these environments.
Oh, very good. Folks, participants, just look at that, the URL where you can also get access to it and start working on all this. I hope this will be very useful for you guys.
Correct. Okay. So just to, you can go in IBM Quantum site and then you can log in, right? So I already logged in, but you could, if you go and I just use my personal IDs. If you go and log out, then you can easily, it asks you to register one. You have to create IBM ID. So you have to go and create an IBM ID for you. And with that IBM ID, you can go and use it. That's all. And you can create an IBM ID account and you can use it free.
I hope all the participants, understand that and, start as a lessons learned from this, start creating an account here and start implementing some of this stuff, whatever we taught yesterday and today, the overall, as part of the overall workshop. Okay, Arshad, there is a question from chat window. Can you just take a look? From Madan Kumar.
This is quiz.
No, there is a question.
From Madan Kumar.
Follow time computer whether the unstructured data. I answered it, right? So
yes.
I answered it. This is for unstructured data. You need to transform into some form of structure. Then only you can fit to the quantum. So every unstructured data has to be transformed into some meaningful form, in a mathematical form.
So what are the other best practices, Arshad, you are suggesting to the whole the two participants here to get onto the quantum computing?
So first thing, go and create an IBM ID and then take a look at these platforms. These are very good simulators they are providing, and with this you can really be able to understand what are how this whole qubit and things are behaved. So, and other things, we do have a Qiskit textbook available free, so you can go, and it's a very good text to understand the quantum computing. So you can go and through those IBM Qiskit textbook, which is an online thing, and they can study on those top of that. And for practicing, and so whole idea is you don't have to. So this okay. 1 second. So I show you one thing. So I show you one thing that see, you see this. There are a lot of simulators already. IBM computers are already running, right? So you use this code. See, you have, if you go you run this code, you see there are a lot of providers: IBM Belém, IBM Lima, Santiago, with 92 5 qubits, and these are things are available, and these quantum computers are accessible to everyone. So you can write some algorithm, you can write some code on that, and then you can go and execute the real quantum systems. So this is a very good place to practice it. This is a very good place to practice the things, and you can go and register your IBM ID, create an IBM ID, and then you can use these notebooks. And there are some references also they being given. I show you on this platform. I show you. Okay, 1 second. Hold on. I just logged out, and that's why it's not. Yeah, it's launching. So if you see this, if you once you logged in, you see there are Qiskit book is there, right? You can go and get start this exploring this book, right? Qiskit book content and all these things are there, right? You can go and study this book. Also, there are lot of material is there. Right? Qiskit tutorials are there. Quick Qiskit nature, Qiskit machine learning, Qiskit finance, Qiskit experiments, and also we have all these example notebooks are available here. So you don't have to go anywhere. You have a complete book is there, complete examples are there. You can go and study from here directly. There's the textbooks available. You can go and study the content, all the things from here, textbooks.
Yeah, team, listen to this. Actually, the participants, there is I mean, you have lots of information on our IBM website. Just go and create an account. I want to see, there are like hundreds of accounts created, and people start using it. Probably once in a month or something as a follow-on to our workshop, our initiative. Even setting up an hub in PSNA, we can do a e-meet or something to discuss further on this. Arshad, there is another question from the chat window. Where can we find the code for Shor's and Grover's algorithm?
It's available in the Qiskit, I think so.
Let us get a.
They're into the Qiskit channel. I show you.
Answer from Arshad. Oh, thank you for. Oh, see here, there are lots of information already available.
So you see this in this Qiskit we have algorithms, right? So we have Grover algorithm, right? So see, go into, you have an account, right? Once you get into this account, go to Qiskit tutorial, right? You go to Qiskit, and then you have algorithms. You see algorithm introduction. You have a Grover's algorithm, right? Grover's example, factorization algorithm. So see this. This is algorithm which is explained everything, and we have every code is written with an explanation on top of that, right? We have already here, right? Similarly, for shows also tutorials. Shows algorithm. Major circuits. In this VQA convergence algorithm introduction, in this you should be seeing the source also. VQE in quantum construction. Factorizer. So factorizer is ultimately Shor's algorithm, right? So you find it, right? It saves as a factorizer. So this is a Shor's algorithm. You can find the Shor's factorization algorithm and you can see this, right? Got it? Grover's algorithm, Shor's algorithm, and this is quantum approximation algorithm. This is VQE usage. Correct?
Yeah.
This is what factorizes is a Shor's algorithm.
Is it necessary to install the QScript here and then as well as the also IBM Quantum?
No, so IBM is completely a platform as a service. You don't have to install anything. Everything is pre-installed. It's just a use. Come in, create your ID and just use it. That's all. You don't have to install anything.
Okay.
So actually, you have to. Yesterday, Abhishek explained everything to get you an idea what is Qiskit and how it could be installed locally also.
Oh.
But there are either you can go and install locally also and do it. The things it provides you offline simulators also, or if you have a good internet connectivity, you could work online. Then you can go and directly work on IBM platform.
IBM.
That is also
So it works in the cloud.
Sorry.
It's work in the cloud, IBM cloud.
Yeah, this works in the cloud, right? This is IBM. This works in a like Google Colab, right? Everyone I think
yes.
for Google Colab, right? So you can go and put your code and everything is provided by them as a Google Colab platform. Their machines and servers and RAMs and GPUs. So in a similar way, you can see that we have a 8 GB of RAM available with for 2070 I'm using, and you can see we have a 6-core CPU available. Right? So like that, we could go and use it. It's similar to a Google Colab from the IBM for the quantum environments.
I think I have seen some research papers. Some of the researchers, they are working with the Qiskit with the IBM and they are given the simulation and they showed in the journal publications. And some of the people, they are working with the from the Google, no? Google, they are having the CRIC.
CRIC, CRICQ.
CARQ. They are using the CRIC to demonstrate and they given some papers with this. And whether the same, if I take a problem and if you work with the IBM Quantum Lab with the genetic algorithm or optimization problem, any neural network, machine learning, and if we work with this, how this could be, whether definitely there will be some differences in our answers, no?
Right. So see, it's similar. It's something like every environment. So it's like sklearn. If you talk about sklearn, so think about that in a deep learning area, right? We have TensorFlow, we have Python, we have Caffe. Everything is a deep learning framework, but it's a different implementations.
Yes.
Correct? It's a different. So in a similar fashion, every company means Microsoft or Amazon, Microsoft or IBM Qiskit or Silk, everyone has their own quantum computer and have their own APIs. So definitely there will be some minor differences between all those things. It's not you just developing something and port in something. It's not should be not like that. But results also there could be some minor things, but I believe it should not be much difference as an output.
They'll accept the research publications. The faculty members are doing research, so they'll accept. If they work with either in the IBM or in the Google, they'll accept the paper. Is it?
Correct. See, the whole idea is, see, underlying concept is same. So if you talk about a deep learning concept, so ideally you developed in PyTorch or ideally developed in TensorFlow, the deep learning concept would not change. Correct?
Yes. Yes.
OOPS concept never changes either you develop in Java or develop in .NET. The fundamentals of OOPS won't change, right? So it's a whole idea of concept. The concept of superposition, some concept of entanglement, concept of qubits, concepts of,
Yes.
but it's not going to be changed. The only thing, the API got changed, implementation got changed, but the underlying concept never changes.
Yeah.
So everything is accepted. No one can deny or any other facts.
Okay. I think the participants, I think there is a feedback, and as the quiz question is shared here, you can answer the questions, and the first three, the winners will get a T-shirt and as well as the certificate from the IBM Open Power. I think we have the mail IDs and as well as the designation and everything is available with us. Therefore, I request all the participants to fill this feedback form immediately, so that you will be getting we can take with the first three prizes, and then the remaining things we can send an e-certificate to your mail ID also. And e-certificate, if possible, I think we are providing the hard copies also too. So the excellent presentation, Arshad. I think you have very clearly given the practical, how the algorithms is taking place in the quantum. So we talk about the classical computers. I think the faculty members and all researchers are studying with these kind of algorithms here. But I think you are given the demonstration how this could be converted into all the quantum computers, and the quantum computers is going to take place much the excellent role in the research aspect also. So many of the researchers will start working on, and I have gone through some of the Elsevier papers also, the physical letter, neural network, genetic algorithm, these kind of things they are concentrating, and optimal control also, I think they are concentrating on this. So in this juncture, I think I thank all the resource persons. I think today morning, Sir has also given a wonderful lecture, and as well as Arshad, and yesterday also we had a wonderful session with Mr. Ganesan, sir. Thank you very much.
Thank you.
Thank you very much for organizing the entire, coordinating the entire the 3 days international IBM Open Power with the collaboration with the PSMA College of Engineering Technology in the quantum computing and application. I think really participants will definitely enjoy. And from this, definitely we'll be having some minimum 10 to 15 publications. So later, I think we can do some work with as you suggested, the IBM hub, the quantum hub for the South India. I think we can after seeing the lot of activities, we can do wonders in this new era of computing. So thank you very much, sir. Sir, you want to say?
Yeah, of course. Thank you for giving us a great platform, and also, it's our pleasure that, we want to share all the technologies, whatsoever happening in the world. And as we speak, there are a lot of other things also from IBM, we do demonstrate, from the silicon to the application, like SoC, system on a chip development, design, and enterprise AI kind of a solution, cyber security related solution, and also adding a few instruction set at the processor level. There are, a lot of, things, which are going, in our, in the world of, technology. And, with this, I want to share, a summary of, what we have done, the last 3 days. And, definitely with the platform, whatever we have right now, it's very good. We can reach out, the whole India, like, South India, North India, and many Indian states, and, the communities, we can reach with the vehicle, whatever we have built so far. And as part of, the 3 day session, definitely, the people would have understood about what is classical versus the quantum physics, brief of quantum theory and experiment in quantum physics, quantum teleportation, what is quantum computing, and why do we need quantum computing. And we do have in this quiz also some of the questions, whoever answers it right, whoever quickly answers it and send it to us, they'll get the, definitely the reward. Because these all, to test your, it's not just to test your knowledge. Basically, whatever time you spent on that, whatever time the presenters and the organizers spent on that, there is a return on investment. The way you go and, respond to the answers, I mean, quiz, we will be very happy with that. And that's where, we get the credits, nothing else. And what is, and as part of the journey, whatever the last 3 days, the bit in classical computer and qubit and in quantum computers and quantum states and qubits, atoms of computation representing qubit state, single qubit gates, multiple qubits, entangled states, quantum circuits, classical computation and quantum computer, and also Arshad today and Satyanandan, Professor Satyanandan today explained about quantum machine learning, and also the introduction of to quantum algorithms like Dosh-Jozsa algorithm, Beristian, Wazirian algorithm, Simon's algorithm, Shor's algorithm, and Grover's algorithm. All these things, one shop, go to IBM site, quantum computing site, and get access to it and start learning. And this way, definitely, you can expand your horizon at a world level. There are like 190 countries, who are getting involved in this quantum as we speak right now. And, you also get an opportunity to work on that with us. So get on to it. And also we have the summer quantum school fellowship. There are a lot of other organizations will be announcing these kind of fellowships. See here, as Dr. Vincent said that, more papers and more publications and more conferences, if you attend, these fellowships and all, you also, will get an opportunity to, work on it. It's basically one of the applications. What I see here is actually applications are still open for 2022 school, the quantum summer school at Los Alamos National Laboratory, LANL. I used to work, work on some of the solutions, 10 years back, along with IBM on that lab. So there is a link already available. Take a look at it and then see anything, you can qualify for that. If it is not the, at least learning purpose, take a look at it. We did put it in the brochure also. This kind of summer school is not only one, but there are a lot of summer schools will come in and, start looking at it and start applying for it. When you apply for it, only you will get a lot of experience, and they'll look at, the skills, what you have, linear algebra kind of skills and the programming, in Python, the modeling, and also the quantum mechanics, of course, and also the leadership in research and development, making, providing suggestions and, getting into this kind of workshops and, asking questions, and also more interactive, and also the presentation skills, whatever you learn, you want to share that also. There are a lot of opportunities are here, and, take a look at that, the LANL Quantum Computing Summer School Fellowship. It's like a kind of a grant, they are giving for people to, people who are doing junior and first year graduation, who can go there and, and study there for, do the internship for nearly like 8 weeks. That's an amazing opportunity for people to work on that. And that is actually done by, all 3 companies, D-Wave System, Rigetti, and IBM. So there are like only 20 students will get selected. So hopefully, whoever, have got some skills on quantum, they can apply and, see how you can get onto this kind of a race and get up to the speed on, getting the, the fellowship while you are studying in your college. So this is a great opportunity for students and faculties, who have got, some international speakers as well as national speakers for last 3 days to learn about, fundamentals to solution algorithm, on quantum. And this is not the end. We are going to continue the journey with the Quantum Hub and, many other quantum related activities along with other classical computing activities too in PSNA. With this, I'm closing. And sir, you want to address a few things and then we'll close it?
Yeah, please kindly unmute the Dr. Shivagami madam, Dr. R. Shivagami. She formally says the vote of thanks. Coordinator.
Shivagami. Hold on.
R. Shivagami.
R. Shivagami.
Yes, sir.
It's not easy to find R. Hold on. Shivagami. Shivagami. Shivagami Raja. Okay.
Yes, yes, sir.
That's actually, yeah. That's a keyword. Okay, welcome back, Shivagami, for giving the vote of thanks.
Dr. Shivagami, Professor of IT Department, is pronounce the vote of thanks. Ma'am, you can unmute. Yeah, please.
Ma'am, you can,
Yes,
yeah, go ahead, ma'am.
thank you. So it is a great privilege for me to propose a vote of thanks to all those who have contributed in one way or the other to make this program a success. So first of all, I would like to thank our chairperson, Tirumadi K. Dhanalakshmi Ammal, our pro-chairman, Thiru R.S.K. Raghuram, and principal Dr. D. Vasudevan for permitting us to conduct this 3-day international workshop on quantum computing and applications. And also, I would like to thank our chief guest, Mr. Ganesan Narayanasamy, and today's resource persons, Professor Satyadyan and Mr. Arshad Mohammed, for sharing their knowledge with us. The session was quite interesting and informative today, and we learned a lot from this 3-day international workshop. So thank you all for your valuable contribution. And further, I would like to thank all our participants who effectively took part in this workshop and also who has made this workshop a grand success. So thank you one and all. Thank you.
Thank you, madam. It's a very nice session, sir. I think maximum, yeah. All the 3 days participants were very eagerly attended.
Yeah, I'm eagerly waiting for the winners of the quiz program.
Yes, sir. I think we'll share in the. I think once
probably in your LinkedIn, you can post it in PSNA website.
Yes, sir. Yes, sir. I'll post it in our PSNA CD website. I'll complete the report and as well as the winners and all the things. I will post it by tomorrow, Monday, sir. Monday.
Okay, sir. Very good. Thanks a lot.
Thank you. Thank all the participants. Thank all the teachers. Maximum the teachers from the American College, Madurai, and Sastra, VIT, and PSG Tech, and as well as the Bannariam Institute, and Velamal Engineering College, and Muthayamal Engineering College. Many of the faculty members were participating regularly the last 3 days. So I thank all the participants, especially the faculty members, research scholars. I think this is a tough time. Last 2 years, we are working on the COVID. Due to the COVID, we are working on the online. But we got bored through online. But the learning is taking place, compulsory. Therefore, we are expecting our students and as well as the teachers to learn. Teachers to learn the new things. Then only we can make our students to learn. So this aspect, we have to compulsory work. And the industry people also quite interesting come here and they are giving they are putting their effort. So on behalf of the organizing committee, on behalf of our pro-chairman, especially our pro-chairman, sir, when I asked him the last week, immediately agreed and he has given the entire permission and he is very much interested working with the IBM and he is very much interested to create a hub over here at PSNACT, our pro-chairman, sir. And also our principal, sir, is also much appreciated and he has appreciated our work. And he is during his busy schedule, I think he has given the presidential address day before yesterday. So I thank one and all, and especially a special thanks to Ganesan sir. We are coordinating for the last 4 to 5 years, and definitely this will go again and again for the welfare of the community, the student community. So if the student communities are getting knowledge, definitely the next generation will be in the again, they'll go in the higher level and next level. So thank you very much, sir.
Thank you, sir. Thank you all.
Thank you.
Thank you. Thank you very much. I'm closing the web workshop.